All right, so if you did not take your midterm exam, all right, don't think that it's over, you failed, all that stuff. Instead, email me if you didn't take your midterm exam, and we'll work something out. There's going to be a penalty involved, okay? But I'm not just going to make it black and white where if you didn't take it, you missed it. Tough luck. This semester I'm going to try something different and actually give students more of a second chance on something that is that important, although again with a penalty. So if you're hearing this and you didn't take the midterm and you think you're going to fail this class, just reach out to me, talk to me, and we'll work something out. And I believe that's it, along with that announcement I said about the homework. So let's get started. Today's 3.2. We're going to be talking about the properties of a function's graph. All right, so we're going to be dissecting a graph and breaking it down into all its little components so we can fully understand what we're looking at when we look at a graph. And again, as I mentioned before, we are moving towards being able to look at a function, an algebraic function, and be able to graph it in our head. For the most part, right? There are some difficulties involved, but we'll be able to do it at a very rudimentary level. But anyways, moving on, it reads in section 3.1 we discussed that every function has a graph. Oh yeah. I then forgot how to instruct. It's been so long between spring break and last week's final or midterm. Forgot to snip it onto this. Alrighty, so again, starting here. An intercept of a function is a point on the graph of a function where the graph either crosses or touches the coordinate axis. Of course, we know that as an intercept. We talked about the intercepts being represented as ordered pairs. We also talked about the y-intercept is the y-coordinate of the point where the graph crosses or touches the y-axis. If a function has an intercept of the point 0, b, of course 0 being the x-coordinate, right? Because we are on the y-axis, then b would be my y-intercept. And then likewise the counterpart here would be the x-intercept. We know it as the point a0. Okay, again 0 over here being how far up and down we're going on the y-axis. Of course we're going neither up nor down, so we're going to be strictly on the x-axis, and we're going to be exactly where a is. And then the y-intercept, a function can have at most one y-intercept. The y-intercept exists if x equals 0 is in the domain of the function. Of course, we'll talk more about that as we move forward. I looked at this section. It's a very thorough section involving functions. So let's go ahead and begin here. All right, I'm going to go ahead and snip the actual function. Maybe not the solution, even though I guess the solution is a part of this, isn't it? But we're going to put it up here just because. Alrighty, so this problem reads, find the y-intercept of the function f of x is equal to negative 3x plus 2. Okay, so how do we find the y-intercept? Alright, well in order to find the y-intercept, we know that we must substitute 0 in for x, right? This was something that we did in previous section. To find the x-intercept, we set y equal to 0, and to find the y-intercept, we set x equal to 0. So let's go ahead and set x equal to 0. So we've got not f of x, and so we're going to put this as 0 here, just to really denote what we're doing. F of 0 is equal to negative 3 times 0 plus 2. Okay, so what I did here is I replaced all the x's in this function with zeros because we're wanting to find what happens at x equals 0. Right. Anyways, we do the arithmetic here. Obviously, negative 3 times 0 is 0, so we have 0 plus 2, so we have simply 2. Okay, and then of course this 2 right here is what my y-axis is, or my y-intercept is. Okay, and my coordinate point would be, okay, I plugged in a 0 for x, so it's going to be 0 for the x, and then I got a 2 out. Okay, so my y-intercept is at 2, or at the coordinate point 0, 2. And of course we can see that up here. My y-intercept, where I cross the y-axis, is indeed at 0, 2. And all I did was plug in 0 for x. Right, that's all we have to do every time. Okay, and then we're going to talk about the x-intercept. Now the x-intercept is a little bit harder. Not hard, it's a little bit more tedious. All right, so let's see. I wonder if I can. Okay, well, I probably should have maybe. Whoa, probably should have maybe put this on the next page above our problem, but it's just gonna have to be what it is because I don't feel like moving all this around. But we talked about the y-intercept and then we did an example. So now we're gonna talk about the x-intercepts. All right. So a function may have several, or even infinitely many. So we could have an infinite amount of x-intercepts. One such function that some of you may or may not be aware of would be simply the sine function. Right? It just does this over and that's pretty good actually. It just does that over and over and over from negative infinity to positive infinity, and it crosses the x-axis an infinite amount of times. Okay. So anyways, moving on. The x-intercepts, also called the real zeros. So x-intercepts and zeros, they are interchangeable. Again, I guess depending on the context. Not I guess. It is depending on the context. Can be found by finding all real solutions of the equation f of x equal to 0. So what we have to do is we have to solve the equation for 0. Now, here's the thing. We've done this the entire semester. We just basically set our equation equal to 0, and then we move from there. Okay. Although a function function may have several solutions. Several zeros, sorry. I don't know. All right, let's just read it as it is. Although a function may have several zeros, only the real zeros are x-intercepts. Yeah, that doesn't make sense. I thought maybe it was like, 2 words. Yeah, whatever. The only real zero of f of x equal to negative 3x plus 2 is x equal to 2/3, because the solution to the equation negative 3x plus 2 equals 0, so again we are equating the equation equal to 0, is x equal to 2/3. Notice from the graph in figure 5 that the graph crosses. Okay, so let's give us a figure 5 here. Oh, yeah, figure 5, that was from the previous example. Okay, but we'll put it here anyways. It says, notice that the graph in figure 5, that the graph crosses the x-axis at the point 2, 3, and 0. And of course, that is true. So what we did here was we just solved the equation from the previous page. All right, we solved that for 0, and we see our x-intercept. Okay, but let's do. I'm pretty sure we're going to do one that's a little bit harder. All right, we're going to do 2. It's a little bit harder. And I can probably tell I'm not going to like B that much. Alrighty, so it's these problems read: given the functions below, find the x-intercepts and the y-intercepts if they exist. Okay, so we have to find the x and y-intercepts. Now, the y-intercepts are always the easiest to find because there's only going to be one y-intercept, and you basically just have to put zeros in all the x's, and that's it. All right, and the reason why that's only going to be one y-intercept is because we know a function must pass a vertical line test, right? Like we cannot have a function have 2 points on the vertical axis. Well, if we were to have two y-intercepts, something like this, right? And of course, this is not a function because it doesn't pass the vertical line test. So that's why we can only have one y-intercept. Okay. With that said, let's go ahead and begin the process of finding the y-intercept. We'll obviously start with A. Okay, and the y-intercept is going to be super easy. What we do, again, let's do this y, just to note that we're looking for the y-intercept here. We got f of, and again, we'll just go ahead and put in f of 0, okay, because again, all we're doing is plugging in 0 for x everywhere. So this becomes, this is going to get tedious, but I got to do what I got to do, right? 0 cubed minus 2 times 0 squared plus 0 minus 2. Okay, now that's pretty easy, right? Because what happens here is this becomes 0, this is 0, this is 0, so all we have left is negative 2. So my y-intercept for A is at the point 0 and negative 2. Okay, so that's the y-intercept. Now the x-intercept is a little more tedious, and luckily for us, we have to recall a lot of the algebraic manipulation that we have been doing so far this semester. Okay, so what do we have to do here? Okay, so real quickly, we've learned that the notation f of x and f of x and y, they are essentially interchangeable. Okay, because y is the output, and the output is also denoted as f of x, the function at x. Okay, so what we can do, okay, is take that knowledge, and we can essentially rewrite this equation to 0 is equal to x cubed minus 2x squared plus x minus 2. Okay, so all I did was basically change this f of x into a 0. Okay, so once we did that, I know that I need to now solve for x. Okay, well, how do I solve for x? Well, again, this is just, we've done this for the first 2 chapters. We've solved equations like this, right? So first things first, we did a lot of quadratic equations. So, you know, we learned how to do the square root method. We learned how to factor. We learned how to do the quadratic formula, all that good stuff. Okay, well, lucky for us, this is not a quadratic equation, is it? Okay, because this is as a 3rd degree polynomial. Right? Well, here's a rule you need to write down. Okay, if you see 4 terms in an equation, the very first thing you need to think is factor by grouping. So this is 1 term, 2 terms, 3 terms, 4 terms. So the first thing that I'm going to think whenever I see 4 terms is factor by grouping. Okay, so I'm going to split it down the middle. Split it down the middle. And I'm going to factor the left side, and I'm going to factor the right side. Okay, so the left side looks like I can factor an x squared out. And let's fix that up a bit, x squared. And what remains would be, looks like an x minus 2. Okay, and then the right side, I need to factor out, it looks like I need to factor out a nothing, just a positive 1. So we're just going to factor out a positive 1. Okay, so I factor out a positive 1, what remains? Well, just the same old equation. Okay, now I'm going to snip this and put this on the next page. We'll continue along. Okay, and then of course we know we can factor this into x squared plus 1 and x minus 2. Okay, and then of course if we solve this equation for x, it appears, okay, so the first one would be x is equal to a positive 2, which is this one, right? Well, the first one, it looks like we're going to have to have an imaginary number, right? And again, all we're doing is setting this equal to 0. It's been a minute, so I'll actually go ahead and write this out for you real quick. Okay, so to solve this, we'd say x minus 2, we'd set it equal to 0, and that's where we get x is equal to 2. Okay, so we have one solution being x equals to 2. And then the next solution, this one, recall we're going to have to do x squared plus 1. We're going to equate it to 0. We've got x squared is equal to negative 1, and then we take the square root of both sides. So we're going to have x is equal to the square root of negative 1, positive or negative, sorry. Positive or negative square root of negative 1, or we know that as plus or minus I. Right? So that is my solution. So plus or minus I. Okay. Now here's the thing, though. These are supposed to be my X-Intercepts, correct? All right. Well, having an X-Intercept at 2, well, that makes sense, right? At the point 2, 0. Okay, I go to the right 2 on the x-axis. That sounds like that's a normal X-Intercept. Okay. The problem here, though, is this right here. I have a plus or minus I. And I don't know about you guys, but I don't know how to graph I, at least not in college algebra. Okay, we can't really graph i's in this course because we're not dealing with the complex plane. Okay, so this means that my X-intercept, my only X-intercepts are going to be at 2. Okay, or in other words, the coordinate would be 2, 0. Okay, that's my x-intercept. So my y-intercept was 0, -2 at the point 0, -2, and my x-intercept is at the point 2, 0. Okay, let's do B. Hope it's not as bad as it looks. Did I? Okay, good. All right, so B. Okay, so again, the y-intercept is super easy to find because all I have to do basically is just say, okay, we're going to say nope, nope, nope. Oh, well, actually, true, we would say nope as in 0, but we also know that 0, we cannot plug in a 0 for x. Okay, so let's actually go back to, which one of these was it? There was something here that talked about the domain. Oh, there it is, yeah. Okay, so let's look down here. It says a function can have at most one y-intercept. So it can have at most one y-intercept, and we talked about why that is because, you know, the whole concept of a function passing a vertical line test. The y-intercept exists if x equals 0 is in the domain of the function. Okay, so what that means is if it's in the domain of the function, if we are allowed to use that, that number. Now here's the thing. All of you should have watched 3.1, okay? If you haven't, and honestly, if you miss any sort of lecture, I would suggest obviously watching the lecture, but I mean, I've been in your shoes. I know what it's like. You don't feel like sitting down and watching a 90-minute video. Put the speed on 1.5 times, okay? Because I do ramble a lot, whatever. But if you put the speed on 1.5 times and at least give it a watch, you are better off than not watching it at all. Okay, and in 3.1, I discussed something what I call my domain Bible. Okay, please watch 3.1. You will not fare well at all in this section if you do not watch it. Okay, but anyways, we talked about what was my domain Bible, meaning that, you know, these are the values that I can use in a function. So that's what this sentence is saying. The y-intercept exists if x equals 0 is in the domain. Okay, if we're allowed to use that number. Now let's look at this example. And I was dreading it because I was like, oh, geez, I hate fractions just like anybody else. Okay, but the thing is, if we look here, we see that 0 is not in the domain because if we plugged in 0 everywhere. Okay, so let's go ahead and try. Let's go ahead and do that. Okay, so obviously, you know, this just becomes 0, this just becomes 0, and this just becomes 0. But this 0 is a big deal because we cannot have a 0 in the denominator. Okay, 0 is not in the domain of this function because we cannot use it. Okay, it becomes undefined. All right, so what that means is this function has no y-intercept. Okay, so we've got no y-intercept, no y-intercept. That's a fancy looking N, isn't it? Looks like ho. Let's actually change that, or at least fix it. No. Okay, so it has no y-intercept. Okay, well now we can move to the x-intercepts. Well, x-intercept, what we do, again, we're just going to set the equation equal to 0. So we're going to have 0 is equal to 2x squared minus 7x minus 4 all over x cubed. Okay, so again, we have to solve for x. Well, hopefully I really get my point across that, you know, I was in your shoes as a college algebra student. When I see fractions, when I see decimals, my brain's like, ugh, okay? But it's really not that bad. And here's a good example. I was dreading doing B because I was like, ugh, a fraction. But it's not that hard because in order to begin this, I need to clear that fraction, right? So what's the first thing I'm going to do? Well, I'm going to multiply both sides by x cubed. And if I multiply both sides by x cubed, then my equation is just going to become 0 is equal to 2x squared minus 7x minus 4. Alright, and that's it. And let's fix that 4 up. And at this point, we can do one of two things. We could either factor it, or we could do the quadratic formula. Okay, and as I've told you before, if I can't factor this in my head within 2 to 5 seconds, or was it 3 to 5? Within 3 to 5 seconds, then I'm going to jump straight to the quadratic formula. But I think I could factor this. Yeah, but let's actually just go ahead and jump to the quadratic formula to really drive the point home. So let's go ahead and snip this and put it on the next page. Okay. Alrighty, so we know my quadratic formula would be x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. Okay, so if I were to fill these in, I would have negative b, so it's going to be a negative 7. I'm probably going to run out of room. Plus or minus negative 7. Yeah, I'm going to run out of room. Shoot. We'll just do it underneath it then. How about that? Or you know what? Let's actually just fill in the blank. Let's just fill in the blank. That might be easier. All right, so a negative b, so it's going to be a negative 7. So negative 7. So that's going to be, we'll just go ahead and put positive 7, I guess. And then we have 7 squared, negative 7 squared. Well, this even looks, whatever. We'll stick with it. And then minus 4 times a times c. So a times c is going to be, a is 2, and c is negative 4. And then multiplied by 2, and then 2 times a down here. Well, 2 times a being 2, so we've got this. Okay. All right, nice. Now we can say 7 plus or minus the square root of, let's just do some mental math. We have negative 7 squared is a positive 49. And it looks like it's going to be negative 4 times negative 4 is a positive 16. 16 times 2 is 32. So 49 plus 32 is 81. And it's going to be all over 4. Okay, and then let's continue this over down here. We have 7 plus or minus, well, square root of 81, that's just 9, all over 4. And then so we're going to have 16 over 4, because 7 plus 9 is 16. 16 over 4 is 4. I'm sorry. Yeah, 16 over 4 is 4. Let's put an arrow there, actually. So one of my solutions is 4. The other one would be 7 minus 9, which is negative 2. Negative 2 divided by 4 is going to be a negative 1/2. Okay. So these are my two X-intercepts. Okay. And if we put this in set, let's put them the other way. Let's do it the other way. Negative 1/2 and 4. We're going to put curly braces there to denote that this is a set. Okay, so the X-intercepts are the set negative 1/2 and 4. Okay, now if we were to say that these are the coordinates, the points, okay, well then they would be negative 1/2 and 0 and 4 and 0. Okay, so that's how we do that. All we did was find the X and Y intercepts of both those problems. It sure seemed like a long time, didn't it? They were pretty simple solutions. Let's just chalk it up till I explain things like crazy. Alright, now we talk about the domain and range of a function. Alrighty. So again, we reference 3.1. Please go watch 3.1. We see that every function has a graph. Figure 6 illustrates every function. Okay. Figure 6 illustrates that how we can use a function's graph to determine the domain and range. Okay. So when we look at a graph, okay. Well, it would be like a graph. All right. Everywhere where it exists horizontally is going to be the domain. Okay, so this squiggly line right here, it only exists from A to B. Okay, it doesn't exist outside of a to b at all. Right, that is what we call the domain, the interval of the domain. Okay, and in our example, or in our well, yeah, I guess that example, notice how we're using closed circles here, which means that we are including them, and therefore you see up here the interval is from a to b, where we include a and we include b. Okay. Now the range is just the, I'm going to say the opposite, but it's the exact same except it's on the y-axis. Okay. So everywhere where this squiggly line exists vertically, that will be our range. Okay. And notice how it goes all the way down to this little dip right here. Okay, which we denote as C. And it goes all the way up here to this peak right here, and we call that D. Right. Same thing, excuse me, we don't have open circles or closed circles to define. One second. Oh shoot, new headset, so I don't think I muted it when I lifted the mic up, sorry. But anyways, we are including D and we are including C. Okay, so same thing, we use the bracket to include them. Okay, now again, I understand that, you know, A, B, C's, and D's are pretty much in one ear and out the other for many of you. So let's go ahead and do us a nice hardcore example here. Okay. Alrighty, so it reads, use the graph of the following functions to determine the domain and range. Okay, so let's just start with A. Right. So we're going to say the domain. Okay, so we're just going to denote this with a D. All right. So the domain is going to be, right? Again, it's where we exist horizontally. Okay, and it looks like we exist from right here to right here, right? From -2 on the x-axis to +4 on the x-axis. All right. Well, we exist from -2 to +4, so let's just go ahead and write -2, +4 real quickly, even though we'll deal with the parentheses and brackets here in a minute. Well, now, I guess. Alrighty. Well, if we're existing from -2 all the way to +4, right, that is true, okay? But what do we put? Do we put parentheses or brackets there? Well, right here, it looks like we do indeed go to -2, but we don't actually touch -2, okay? We go to -1.999999999. Okay, we don't actually touch -2, but over here we do actually go to 4. Okay, so what we're going to do is we're going to put a parentheses around the -2 and a bracket around the +4. Okay, now the range. All right, so again, the range is where we exist vertically. Okay, and it looks like we exist from down here at the x-axis all the way up here to the 6. Okay. Alrighty, so this looks like we are indeed, looks like we're actually touching the x-axis, okay? So we're going to put a 0 here, and then we go all the way up to right here, which would be 6 on the y-axis. So we go all the way up to 6. Alright, and it looks like I said, it looks like we touch the 0. Whoa, wrong color. Looks like we touch down here at 0, and we are definitely touching up here at 6. So we're going to be using a bracket for both. Okay. All right, next B. The domain of B. Okay, so it looks like we are existing from right here at -4 all the way to, well, it looks like right here at 5, we're going to be getting infinitesimally close, but not actually touching 5, right? Looks like we're going to go into 4.9999999. Okay, so it looks like, again, on the x-axis, I should have drawn it from the x-axis. It looks like we're going from here to there. Well, I could have done better. From there to there, okay? So we're going from -4, but it does not look like we are including -4. So we're going to be putting a parentheses around -4. We're going to be going all the way to 5, and it does not look like we're touching 5, so we're going to put a parentheses around 5 as well. Okay, so that is my domain. Now my range, again, my range is vertically, and it looks like vertically, it looks like this arrow is denoting that we're going straight up. Okay, so this must mean that we exist on the y-axis all the way from down here at -3, okay, all the way up to infinity. Okay, and again, it's where we exist on the y-axis. So the range here, okay, looks like we're going from a -3, but we're not including it because it's an open circle there. So from -3 all the way to infinity. Okay, and then C, my domain looks like it's, again, we're looking at the x-axis. Okay, from it looks like it's going all the way to -infinity, so that's a good start. So we're going to go ahead and put that there. Okay, and of course the infinities always have parentheses. So it looks like we're going from -infinity, and we're going all the way here to, looks like a +3, okay, where we are at on the x-axis. So we use the x number there to 3. And it looks like we include it because it is indeed a closed circle. So we're going to include it, and therefore put a bracket. My range, okay, again, looking at the y-axis. Okay, so it looks like we're going from -2, but we're not actually touching -2. Okay, because again, looks like it's getting close and close to close, but it's not actually touching it. So it looks like we're going from -2. We're not actually touching it, all the way up to, looks like 4, and we are touching it because we have a closed parentheses. Okay, and that's it. When we talk about the domain, we're dealing with the x-axis, and when we talk about the range, we're dealing with the y-axis. Okay, so in that context, you're going to be looking at the x and y numbers of what you're actually looking at. Okay. This part's pretty simple. Right. So a function f is said to be increasing on an open interval if the value of f of x gets larger as x gets larger on the interval. You know what? I don't have to read all that. I mean, you can read it, but we know when we read we read functions, we read them from left to right, just like anything else, right? From left to right. Well, if we're going down, we consider that decreasing. If we stay the same, we consider that constant, and if we are going up, we consider that increasing. Okay, we've dealt with a concept like this before when we talked about slope, right? A negative slope, no slope, and positive slope. So same kind of idea behind that. And if I recall, this next example should be pretty easy. Alrighty. So it reads, given the graph y is equal to f of x, determine whether the function is increasing, decreasing, or constant. So let's go ahead and discuss where it is increasing. We're going to put an I for increasing. Okay. It appears that it is increasing from, it looks like, oh, that's another thing. When we talk about the increasing, decreasing, constant, we're talking about these intervals. We're talking about the intervals on the x-axis. Okay. So, again, reading left to right, we talk about on the x-axis. This looks like it is going up from, and it looks like negative infinity because this is going down, 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 down. True, but it is slowly going to the left right here, right? Like if we had an infinite amount of time, infinite amount of graph paper, whatnot, we would see that we do indeed go to negative infinity. Okay. So my interval appears like it would be from negative infinity. Okay, and it is increasing from negative infinity all the way up to, and looks like right here at 0. And again, we're looking at the x-axis. Okay, so at 0, when x equals 0, it appears that we have stopped increasing. Okay, so at 0, we're going to stop increasing. Now here's the thing. We put a parentheses here. Okay, the reason why is because we are increasing from negative infinity to 0.000000000000001. Lots of zeros, right? But right at 0, we're actually not increasing nor decreasing. Okay, so that's why I put a parentheses there at 0, right? So that's where we're increasing. It looks like we're also increasing from, looks like right here at -2, I'm sorry, at +2, we're increasing from 2 to 3. Okay, so we're increasing from 2 to 3 on the x-axis. So we're going to say 2 to 3. Pretty easy, right? We just basically look at the graph. We say, okay, we're going up here, we're going down here. Well, we haven't said down yet, but we're about to. Where are we going down from? Okay. Well, again, looking on the x-axis, it looks like we're going down from, it looks like 0 to 2. Right here, this little slope there, we're going down. So we're going down from 0 to 2. 0 to 2. Okay. And then we are constant from, and of course we're only constant in one place here. And it looks like we're constant from, looks like 3 all the way to infinity, right? 3 on the x-axis all the way, oh, what happened? 3 on, oh yeah, I can't write small. 3 on the x-axis all the way to infinity. Okay, that's increasing, decreasing, and constant. Pretty easy stuff. Now I will say, and I've looked at the homework, and I'm really sorry to tell you, but it is very, 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 very tedious. That's just the way it is. I'm sorry. But hey, at least now, if you you know, are unable to complete your homework by Sunday at midnight, you can still do it. It's just for a little bit of a penalty. Again, just trying something new. You guys are my guinea pigs. Let me know how that works. I'm sure my previous courses were like, man, well, how come we don't get to have extended deadlines? But anyways, so when a function changes, we'll start here. When a function changes from increasing to decreasing at a point, okay? Now this notation here, it looks like it's a little complicated, but it's really not, right? It's using c, but you know we're used to x, right? It's kind of the same thing as saying x and then f of x, right? X being my input and then the function at x being my output. But it's using c, you know, just to make sure they are inconsistent and try to, you know, confuse my poor students. Then f is said to have relative maximum at x equals c. Okay, now, you know, honestly, the rest of that basically is just talking about maximums and minimums, right? And again, I could read it to you, and you know what? I guess I will, even though, whatever. So the relative maximum value is f of c, so the function at c. All right. Similarly, when a function changes from decreasing to increasing at a point c f of c, then f is said to have a relative minimum. Okay. So what all this is saying is basically saying, and again, just putting it down to cornbread language, the maximum occurs at the top of what you're looking at. Pretty easy, right? And the minimum occurs at the bottom of what you're looking at. Right. Now, at the same time, this particular example is actually not necessarily relative, but it looks like an absolute maximum, an absolute minimum. But your maximums, your relative maximums, are going to be your peaks, and your relative minimums are going to be your troughs. Okay. And of course, it reads down here, the word relative indicates that the function obtains a maximum or minimum value relative to some open interval. It is not necessarily the maximum or minimum value of the function in the entire domain. Okay, so when we say relative maximum, relative minimum, again, we're just talking about the peaks and the troughs. All right, not absolute maximums, absolute minimums, and we'll see that on probably the next page, the next example. Yeah. Okay. Alrighty, so this reads, use the graph to answer each question. Easy enough. Okay, so A, on what intervals is f increasing? Well, we just got done doing an example like this. All right, well, it looks like it is increasing from -3 to 2, right? It looks like right here let's do blue. From -3 to 2, it looks like we're going up. It also looks like we're going up from 5 to infinity. Okay, so we are increasing from the interval from -3 to +2, and also from 5 to infinity. Right. In B, where are we decreasing? Well, it appears we're going down from here from -6 to -3, and from 2 to 5. Okay, and again, I'm looking at the x values, all right? Because when we talk about intervals, we just talk about the x values. We don't care about the y's, we care about the x's. Okay. So it looks like we're decreasing from -7 to -3, and from 2, and from 2 to 5. Okay. C. For what values of x does f have a relative minimum? Okay. So again, we're simply looking at peaks and trough. Well, for this one, we're looking at the trough, right? The bottom. For what value of x does f have a relative minimum? Okay. So the relative minimums here, it looks like it's right here and right here. Okay. Well, what value of x does f have a relative minimum? Well, the value of x, all I have to do is look at the x values. Okay. My x values are x equals to -3 and x is equal to 5. Those are the values of x where we have a minimum. Pretty easy, right? Well, the next question asks, for what value of x does f have a relative maximum? Okay, well, the relative maximum, again, we're looking at the, well, not necessarily that, right here. Okay, the relative maximum is right here at that peak right there. Okay, we're not choosing this because we're not necessarily going off and you know it's not peak per se, right? We're just looking at where we rise up to a point and then down to a point. This does not rise up to a point. Okay. Likewise, we don't have a maximum over here either, right? Because it's just going on and on and on forever. So the only value of x that has a relative maximum is at 2, at x equals to 2. Okay. And then E reads, what are the relative minima? Well, that's, again, pretty easy because the relative minimum, we gave the x values of the relative minimum. Well, now we're just going to give the coordinate, right? And the coordinate would, well, no, it says what is the value, sorry. So what we're going to do is we're actually going to give the y value, sorry, the y value. What are the relative minimum? So what we would say is E, we have a relative minimum at -2 and at 0, right? That is the value of it. So let's be a little more thorough though. If I recall, I think we have to put this like this: f of -3. Okay, and again, this is just coming from right here, and obviously I'll put f of 5 as well. F of -3. Well, what is the value at f of -3? Well, that's -2. And then f of 5. What is the value at f of 5? Okay, well right here, well that's just going to be 0. Equals 0. Okay, and let's see if we can fit an f over here. What are the relative maximum? Okay, well, and you know, it's kind of the same process. We'll say f of 2. Okay, well, what is f of 2? Well, that is 5. Okay, so C, D, E, and F, they're all kind of the same. It just depends on the context and how it's being worded. Okay, do spend a couple minutes trying to wrap your head around what's being asked in those particular problems. Like I said, they are very similar, asking a very similar question there, but they have different answers. Okay, but hopefully you can put these puzzle pieces together and figure it out within like a minute or two, or you already figured it out. So let's see if let's put this, because this is pretty important. And honestly, I feel like they might word it better. Ooh, where we're going to put that. Okay. Well, that'd be perfect right there, huh? Well, here's what we're going to do. We're going to actually, we'll cover it, but I'm not going to put it in the notes, okay? But realistically, it's what I talked about earlier. It's just probably a lot more eloquently put than the way I did. It reads, in example 5, the value of f of -7 equals 6 does not represent a relative maximum. Okay, because that's what we said. We said right here is not a maximum because we're not going from, we're not rising up to it, right? Well, the textbook says this is because the function does not change from increasing to decreasing at that point. Okay, it's not changed from increasing to decreasing. It's just simply decreasing from that point. All right, that's why we did not consider that a relative maximum. And of course, that is a lot better put than what I said. Alrighty, so next up, even and odd functions. Okay, so the graphs of some functions are symmetric about the y-axis. For example, the graph of these functions sketched are all symmetric about the y-axis. Okay, so you can tell, you know, if you were to take this and split it down the middle, that they are indeed mirrored across the y-axis, right? Functions that have this behavior are known as even functions. Okay, and let's see. This is what we're going to come back to probably later on. I don't know if that actually gives us a definition, but starting here, it says functions whose graph are symmetric about the y-axis are called even, as we said. For any point x, y on each graph, the point negative x, y also lies on the graph. Okay, for any point x, y, the negative of the x lies on the graph. Okay, therefore, for any x value in the domain, what I circled in red there, we're gonna talk about in detail towards the end of this section, I believe. Sorry, so f of x equal to negative of x, f of negative x. Sorry. Oh, it does actually talk about. Okay, good. All right, so we're going to put this definition on a new page, and I actually don't like the way they write it, just a tad. Okay. Instead, here's what I want you to do. I want you to write f of negative x is equal to f of x. Okay, that's what we're going to write because remembering even and odd functions, it's gonna work out so much better if you remember it this way. If you put the f of negative x first. Okay, same thing, but you put the f of negative x first. It'll be so much easier to memorize. Okay, this is an even function, and when you plug in negative x, a negative x value for x, and then you get back the original function, you have an even function. Now again, I know those are words that don't mean much to you, and we'll definitely do examples of that here in a moment. Okay. Next up we have odd functions. Okay, so if we have even, then we also have odd, right? Okay. Well, even functions are symmetric about the x-axis. I'm sorry, the y-axis. Odd functions are not symmetric about the x-axis, right? Because let's imagine for a moment a function that is symmetric about the x-axis, right? If a function looks something like this, okay? There are equations that do look like this, but they are not defined as functions, right? Because, well, it automatically fails the vertical line test, right? So there are equations that look like this, but they're not actual functions, so we don't deal with them right now. Okay. So if an even function is symmetric about the I keep saying that. It's symmetric about the y-axis. An odd function is going to be symmetric about what we call the origin, the middle there. Okay. Again, you cannot have a function symmetric about the x-axis, but an odd function is symmetric about the origin. And what that means is basically what we're doing is we are kind of folding it over the y and then over the x, right? So let's look at this one for example, right? If we were to make this fold over the y-axis, it would look like this. And if we folded it over the x-axis, well, we would go right here, right? Same for this one. If we fold this across the x-axis, it looks something like this. And if we fold it across the y-axis, did I do it again? If we fold it across the y-axis, it would look like this, and then fold it across the x-axis, we'd look like this, and so on and so forth. Okay, so even functions are symmetric about the y-axis. Odd functions are symmetric about the origin. Okay, believe the next set of let's put that in there. Current page. Yes, perfect. Okay. So similar to the even function thing that I didn't want you guys to worry about, we're going to write this backwards again as well. Okay, we're going to say f of negative x is equal to the negative of f of x. Okay. Now again, we're going to come back to that. Don't worry about it. I'll explain it in better detail whenever we do that. Okay. But just remember, that is an odd function. We'll come back to it. Alrighty, so example 6 now. These are really easy, I think. All we gotta do is just look at the graph and say, oh, are we even, odd, or neither? Okay. Well, we're gonna look at A. Well, is it symmetric about the y-axis? Well, no, right? We can't just fold it across the y-axis and it exists as the same form, right? It's definitely not even, and it's also not odd because we are not symmetric about the origin. Okay, we can't fold this across the y-axis and then across the x-axis, so this is going to be neither. Okay, well, B looks like, well, it looks like we could. It looks like we can fold it across the y and then fold it across the x, and we'd have the exact same graph, right? So that means B must be odd, right? And then C, that's very obviously even, is it not, right? You just, all you have to do is fold this across the y-axis, and you do indeed have an even function. Okay, now yes, here we go. Okay, so example 7. So example 7 is where we're going to use what I told you guys about earlier. Okay, so let's go back, and I'm going to rewrite this, but I want to touch on it real quick. Okay, I want you to write this down. An even function. Okay, honestly, if you just write even function and this, you're golden. Okay, obviously the other stuff is important, but it's more in line with the rigors of mathematics. All right, for this course, if you remember, even functions are whenever you plug in negative x, you get back the original function, you're even, and odd function, whenever you plug in a negative f of negative x, you get the negative of the function, then you're odd. Okay, so let's actually, before I try to flesh that out, let's actually show an example of what I'm trying to say here. Sometimes words escape me, as you guys know. Okay, so what I'm going to do, notice how in both of those examples, or both of these definitions, I guess, we have f of negative x. F of negative x. Okay, and actually, let's just go ahead and write that on this page. Okay, I'm going to go ahead and write this on this page. So, an even function is when we use f of negative x. We plug in a negative x, and we get back the original function. Okay, an odd function is when we plug in a negative x, and we get back the negative of the function. Okay, so let's explore what that means exactly. Okay, so let's start with A. Okay, so we're going to start with A, and we're going to plug in a negative x. Okay, so we're going to say negative x, we're going to say negative x cubed. Okay, let's actually do the color coordination here just to really drive the point home. Let's see, do this, f of negative x is equal to negative x cubed plus a negative x. Okay. All right. So negative x cubed. What is negative x cubed? Well, negative x cubed is just going to simply be a negative x cubed, right? And so let's write this out. So if we had negative x times negative x times negative x. Okay, well, negative x times negative x, that gives me a positive x squared, right? A positive x squared times a negative x gives me a negative x cubed. Okay, so that's how I got this negative x cubed there. Okay, so, and then plus a negative x, which is just going to be a negative x. Okay, so now that we've plugged in our negative x values, we have to ask ourselves, okay, so this equation here, is it the exact same as this? No, it's definitely not the exact same, right? Is it the exact negative of it? Okay, well, the original equation has a positive x cubed, this one has a negative x cubed. The original equation has a positive x, this one has a negative x. Okay? It is the exact negative of my original equation. All right? So since it is the exact negative of my original equation, which is, you know, this right here, okay, the negative of my original equation, then I know A is going to be odd. Okay? So just kind of recap, because I feel like this, I don't know, I feel like this is kind of hard to wrap your mind around, especially on a lecture going approaching an hour. All right. In both cases, what we're going to do is we're going to plug in a negative x. Okay. If you get back the original equation, then you have an even function. If you get back the negative of the original equation, then you have an odd function. And A is an example of us getting back the negative of my original function. Okay. Again, because these are negatives of that. Okay, so let's do B. I wonder if I can fit B here. All right, so we've got g of negative x. Again, in both cases, we were plugging in a negative x. That's why I wanted you guys to write the formulas the way I wanted you to write it, right? Because it just, I don't know, it's easier to remember anyways. Okay, so we got this, and then a negative x squared plus 7 times the absolute value of negative x. Okay. So if I were to, well, we will, we do the arithmetic here, okay? Well, 1 over negative x quantity squared. Well, negative x quantity squared is just going to be x squared, right? Anything squared is going to be positive, right? A negative number times a negative number is always positive. So this is going to be 1 over x squared, right? And then same thing over here, we've got plus 7 times the absolute value of negative x. Well, the absolute value of a negative number is just simply that negative number, right? So it's going to be 7 times x, okay? Well, looking at this, is this the exact same as my original equation? It's a little tricky, but it is, okay? Because, well, let's just look at it. Well, first of all, again, an even function, when I plug in a negative number, I get back my original function. Okay. Well, down here, is this the same as this? Well, it actually is, even though it's missing, you know, the absolute value symbols. But it actually is because, well, what is the absolute value of x? Well, that's just x. And that's what this is over here. Okay. So it is the exact same as my original equation, so we can just stop there, right? So that means that B is going to be even. Okay, because it's the exact same. Now let's do, I want to keep this, put this on a new page. Okay, snip that. Oh, that's perfect. All right, now let's go ahead and do C. Okay, so again, we're going to sub in a negative x 2 times, looks like a negative x raised to the 5th power. Well, this just looks all sorts of not fun, doesn't it? Okay. Now, if we do the arithmetic here, well, what is negative 5 raised to the 5th power? Well, negative 5 raised to the 5th power is going to be, I'm sorry, oh my goodness. Negative x raised to the 5th power. Well, negative x raised to the 5th power is negative x raised to the 5th power. And the negative x raised to the 5th power times 2, well, that's just going to be a negative 2x raised to the 5th power. Okay. And then we have a negative 1 over a negative x. Okay. Well, that negative over a negative, right, was just going to give us a positive. Okay, well, let's see. Let's actually really drive this point home real fast. Let's look at this, okay, because I feel like that might confuse some folks. I told you at the beginning of the semester, if you write negative a over b, all right, or a over negative b, that's the same thing as saying negative a over b. Okay, I said at the beginning of the semester, start putting your negatives out front because it makes computation easier and it's a lot easier on your eyeballs for whenever you do get into doing arithmetic like we're about to do now. Okay, because what's going to happen here is if we look at this particular problem right now, okay, right here, let's see, yeah, right here, we've got a negative, and then if I rewrote 1 over negative x, you know, in the form that I said you probably should, then it would be a negative 1 over x, right? And of course, it's very easy to see now that it is indeed a negative negative, or in other words, a positive. Okay, but anyways, positive 1 over x. Okay, so now we're going to ask ourselves, is this the exact same as this? Well, no, it's not. Okay, but is it the exact negative? Well, let's see. Well, this has a positive 2x to the fifth, and this is a negative 2x to the fifth. Okay, this is a negative 1 over x, this is a positive 1 over x. Okay, so C is indeed an odd function because it is the exact negative. Okay, and then D, we're going to have a big G of negative x. Again, we substitute in negative x, and in both cases we substitute in negative x. That's equal to negative x squared plus a 4 times a negative x. Okay. Well, what is negative x squared? Well, that's just going to be positive x squared, and then 4 times a negative x is going to be a minus 4x. Okay. All right. So, is this the same as this? Well, the x squareds, they're both positive, but one 4x is positive, one 4x is negative. Okay, so it's not the exact same, so it's not even. They are not the exact negatives, right? Because again, this one has a positive x squared, this one has a positive x squared, so it's not exact negatives of one another. Okay, so it's not even, nor is it odd. So the only option we have left is neither. Okay, and that's that. Very nice long example. And then I believe this is the last example of the day. We are going to absolutely go crazy and dissect this function. Wow, that's a lot of problems there. All right, let's try, instead of taking up space on some of them, let's try to answer them right here. Okay, because I think we can on a couple of them. So this reads, what is the y-intercept? Well, that's pretty easy. It's right here. It's where we cross the y-axis. So it's going to be 0, 0, negative 2, Sherman. What are the real zeros? Okay, so earlier we said that real zeros and x-intercepts, you know, they're the exact same thing, right? So all we have to do is write down my real zeros. Well, my real zeros are located right here at the x-intercepts, and that's a lot of them. Okay, so it looks like it's going to be at, they're going to be at negative 6, at negative 2, at positive 2, at positive 6, and it looks like at positive 10. Positive 6, positive 10. Of course, and again, these we're going to put this in the curly braces because that's a set. Okay, and I think we're kind of out of room now, so we're going to have to go out here to do the C. Okay, so this reads, determine the domain or range of f. Okay, so let's write the domain first. The domain, okay, well, we're looking strictly at where we exist on the x-axis. Okay, it looks like we exist from right here at negative 7 all the way up here to 11. Okay, so it looks like we're going from negative 7 to 11. So negative 7 to 11. Okay, but that's not the end of the story because, well, we have to use brackets and parentheses, right? Well, it doesn't look like we exist at negative 7, so that's easy, it's a parentheses. And it does look like we exist here at 11 because it's a closed circle, so it's a bracket. And the range, okay, the range again is on the y-axis here, right? So where do we exist on the y-axis? looks like we go all the way down to, it looks like -5. And again, the y, I'm sorry, the range corresponds with my y-axis, so I'm going to be looking at my y number there, right? The -5. Okay, so it looks like I'm going from a -5, and then we include it, so we're going to have a bracket -5, and we're going all the way up to, it looks like 4. It looks like we hit 4 on 2 occasions, so that's pretty good. Okay, so we're going from -5 all the way up to a +4, and that's the range. Okay, oh gosh, this is crazy. What a problem. Okay, so we are increasing from, looks like we're increasing from, looks like from a -7 up to a -4. Okay, so we're going to say from -7 to -4. Oop, not a parentheses there. We're also increasing from, it looks like, we're going up here as well. So from 0 to 4. Okay, and it looks like we're also going up from 8 to 11. So from 8 to 11. That's where we're increasing, and we are decreasing from, okay, it looks like we're going down right here from, excuse me, from a -4 to a 0. Ooh, that looks like a 6. -4 to 0. It looks like we're also going down from a 4 to 8. Okay, and we are not constant anywhere. Okay, so we're going up 1, 2, 3 times, which we got here, and we're going down 1, 2 times, which we have here. Okay, so that takes care of that. And let's go ahead and snip this. I wonder if my snipping tool actually snips my tools there. Oh, it doesn't. Nice. Okay, good. All right, so which one did we just get done with? Good. Okay, so E. Now we're going to be on E. Unfortunately, I didn't erase those green lines there, but hopefully they're not going to bother us. So for what values of x does f obtain a relative maximum? What are the relative maxima? Okay, so my values of x where we are at a relative maximum, it appears that it would be at -4 and +4. Okay, so at -4 and at +4. And then the second part reads, what are the relative maxima? Well, that's pretty easy. Well, what is the value at -4? Well, it's going to be 4. So at f of -4, we are at 4. And at f of 4, we are at 2. Okay, and again, I'm just sitting here, I'm just looking at f of -4 is equal to 4, and at f of 4 is equal to 2. And that is the relative maximum. And then the next problem is probably going to be the relative minimums. So what values of x we have relative minimums? So it looks like we have a minimum at, it looks like at 0 and 8. And then similar to what we did with the relative maximums, we have at f of 0, we have, looks like -2. And at f of 8, we have a -5. Okay. And okay, well, G seems pretty darn easy, doesn't it? Is this even, odd, or neither? Well, this is definitely 100% neither, right? It's not reflective about the y-axis, nor is it reflective about the origin. So this is a big ol' neither. H, for what values of x is f of x equal to 4? Okay, so this is interesting. So where is my function f of x equal to 4? Okay, so right here, where is f of x equal to 4? So I've told you before, f of x and y are essentially interchangeable, right? They mean the same thing, and again, depending on the context, you use one or the other. We could think of this as, where is y equal to 4? Well, it looks like y is equal to y, doesn't it? Where is y equal to 4? Okay, well, we're looking here at the y numbers, right? -2, 0, 4, 0, -2, 2, -5, and 4. Okay, so we're just looking at the y's. right? Well, it appears that we are equal to 4 right here and right here, right? So what values of x? So the values of x where my y is equal to 4 is going to be at -4 and 11. That is an and, believe it or not. That might help out. Nah, it looks horrible. I don't know if that's any better. All right, and then I. What values of x is f of x less than 0? Okay, so what values of x is are we less than 0? So this is going to be an interval here. Well, in some of them. Well, yeah, an interval here. Okay. So it reads, well, for values of x is f of x less than 0. So again, kind of the same as before. I was kind of the same as the problem above it. You can kind of think of this as, you know, for what values of x is y less than 0. Okay. So basically, where are we below that x-axis there? Okay. And it looks like we are below the x-axis from -7 to -6. Okay. From -7 to -6. I'm out of space, and I don't think I'm going to be able to push it in there. So I'm just going to say them if that's fine. And of course, you know, obviously it's being recorded. You can always, you know, hit the rewind button or something. But it looks like we are below the x-axis from -7 to -2. Okay. We're also below the x-axis from -2 to +2, and then we're also below the x-axis from 6 to 10. Okay. I might have, could have. Let's see. No, I'm not even gonna try it. The concept is there, right? And of course, like I said it out loud. We're good to go. But I believe, yes, that does conclude today's lecture.